Okay, everybody in Zoom, can you hear me?
Yes, sir. We can hear you.
Okay, then what's your name in chat?
I believe I was the first person to put the chat.
Huh? You haven't put your name in chat, put your name in chat. That's all I have to say about that. Okay. Now, last thing we dealt with was the cardioid. When the function you're given is written like one of these forms, then it will look. Second, sorry. All right, when you have it written that way, it will look like some form of this, where the point of the heart shape is on the pole. We have if it's in terms of sign, like this one was, then the theta equals pi over 2 is the symmetry axis. And if it's minus the sign, then the bulk of the thing is below the polar axis. And if it's plus sign, then it's just flipped across the polar axis. And so it would be up here like this. So these two are mirror images of each other across the polar axis, where these two are going to be mirror images of each other across the theta equals pi over 2. So instead of being arranged with this orientation, it'll be oriented along here. So it's either coming out this way or going out that way. So it's laying on its side, basically. And that's what happens with those. The graphs are very similar in shape, or they are the same in shape. It just depends on how far away from the origin you end up going. I mean, the pole. And the graph of the cardioid passes through the pole. That's what this last statement says. Now, notice up here it says graphing a polar equation, and it's called a lambicon. I don't know how that funny looking C there is pronounced. I don't know what language it comes from. The C with a little tail on. Is it French or?
I would say it's French, Lamaçon.
Lamaçon?
Or what do I?
I know nothing. Barely know my own language. Okay. So the graph of this is going to look a lot different, and we build it the same way. We pick values to put it. Well, first thing they do here, they check for symmetry and replace theta with negative theta. Well, we know cosine is an even function. So cosine of negative theta is the same as cosine of theta. So we're going to wind up with the same formula. We're going to wind up with the same equation. So it does have symmetry with respect to the polar axis. But we also need to check to see if it's symmetric with respect to the theta equals pi over 2. And so we replace theta with theta minus, with pi minus theta to check for that. And so we do the cosine of the difference of two angles, which ends up being the cosine of the first angle times the cosine of the second. So it's the product of the cosines of the two angles plus the sine of the two angles. And if you're subtracting the two angles, you're adding those two products. Well, the cosine of pi is -1, and the sine of pi is 0, so this part goes away. So this just becomes a negative cosine, so it's going to be -2 cosine, which is not the same. So it fails the test, which means we just don't know. It probably isn't symmetric with respect to theta equals pi over 2, but it could be. The test fails, so it may or may not be symmetric to that line. All right. And then we check for symmetry with respect to the pole, and they do this real quick without. The test fails, both tests fails when you replace R with -R and you replace theta with pi plus theta, the test will also fail for similar reasons. And so since we're dealing with cosine, and cosine is positive, and we're dealing with that it's going to be symmetric with the pole, then I'm just going to look at half of the angles above the pole, and it'll have matching points on the other side of the pole. So from 0 to pi, they look at at increments of 30 degrees, pi over 6, and find out what the function equals at those values. And then they graph them. Well, I usually graph them as I find them. And so the points they found go around like this to here. And then the symmetric point is down here. So it's you look at where it is across the polar axis, where they line up with each other. So then you can graph the other half without having to do any calculations. And then you connect them. It looks like the cardioid, but it does not go through the pole. And just with the cardioid, the lamicon, I pronounce it lamicon, I'm probably pronouncing it wrong, but it, just like the cardioid, it has 4 functions that give this shape. It just depends upon, is it oriented along the polar axis? Is it oriented along the y equals pi over 2? And is the inner point, I don't know what to call it. This also is heart shaped. So the peak of the heart up here is either to the left or to the right of the pole, or it's oriented up right side up, or it's oriented upside down along the theta equals pi over 2. Now, another thing they talk about here is knowing about A and B. Right? In this case, A is the larger of the two numbers. So A plus B cosine, A minus B cosine, A plus B sine, and A minus B sine. For the A and B, the A is larger than the B, and they're both positive real numbers. So you have a lamacon without an inner loop. Now, what do they mean without an inner loop? Well, because sometimes these shapes have an inner loop, and you're going, well, what the hell is an inner loop, Mr. Reed? Well, that's what we're going to talk about now. This is R, is that a 1? 1 plus 3 theta, 3 cosine 3 theta. 1 plus 3 cosine theta is what they have. So we look at again, they check for symmetry. Is it symmetric with respect to the polar axis? Is it symmetric with respect to the theta equals pi, the vertical line? Or is it symmetric about the pole, the origin? And again, we know cosine is an even function, so the cosine of negative theta is just the same as the cosine of theta, so that's going to result in the same formula, the same function. So we know it's going to be symmetric with respect to the polar axis. And then we check the other two symmetries and put in pi minus theta. And because of the nature of what happens there, it's going to be, the sign is going to change between the 1 and the 3 cosine. So we don't know. It could be, but probably is. And then they don't go through the process of doing this last check, but it does have the same outcomes as checking for being symmetric with respect to the vertical line, theta equals pi over 2. And just like with the previous problem, we're dealing with from 0 to pi, and so we find these values going along the way. Please notice that some of these values become negative. So the angle 5 pi over 6 5 pi over 6 goes over here, but we're going to do a negative 1.6 that way. So we're going to end up going in the opposite direction of this angle for these 3 points. So instead of going to the left, we're going to end up going to the right 2 minutes. And that's what it looks like. So that's the first half. So the first half, these points just get plotted normally, and this one winds up at on the pole. Was there one that wound up on the pole? No, there wasn't. I don't think there was. No, none of them had 0 as an R value. But it does end up going through the pole here. And this one here was negative 0.5 2 pi over 3. Well, 2 pi over 3 is this ray. So that means we want to go in the opposite direction with the negative. So that takes us to this point here. Same thing is true with the negative 1.6, 5 pi over 6. Or this isn't pi over 6. This is, what is that? It's 11 pi over 6. And then, so we end up along there, 1.6 units. And this is negative 2 pi, where pi goes that way, but I'm going 2 units in the opposite direction. Now we are going to look for the mirror images. So this point has its mirror image here. So its mirror image is here. This one's mirror image is, it's here. This one's mirror image is here. This one's, we have to go across that the polar axis to get to those mirror images, and then this is its own mirror image. And so it does the same path, just a mirror image of it. And so that's, I'm going to erase my line. And so that's what we have. And here looks better than mine. And so this is what they mean by an inner loop. No doubt, Mr. Reed. Okay. Now, logons with an inner loop are characterized by these equations. It looks just like the equations with the ones that don't have an inner loop. The only difference is now B is larger than A. Right? Because that one was 1, was it 1 minus or 1 plus? It was 1 plus 3, where the 1 is smaller than the 3, or the 3 is bigger than the 1. So whatever cosine or sine is being multiplied by, that number without the sign is going to be larger than the constant out front. Check for symmetry. This has symmetry with respect to the polar axis. Because if I put negative theta in for x for theta, I'm still going to get the same thing. Because this would end up being a negative 2 theta, and the cosine of a negative is the cosine of the positive. Replacing theta with pi minus theta, we wind up with the same thing. Cosine 2 theta. So it is symmetric with respect to the line. Theta equals pi. So it has symmetry, it has both vertical symmetry and horizontal symmetry. And since the symmetric is since it is symmetric with respect to both the polar axis and the line y equals pi over 2, it will be symmetric with respect to the poles. So this one is going to be symmetric with respect to all three. Like a circle is symmetric with respect to all three things. It's symmetric with respect to the origin or the pole. It's symmetric with respect to the horizontal axis and the vertical axis. So let me see, how much do they do? Oh, they only did a quarter of the circle, because all of those points are going to be repeating again. I don't know that I would have done it that way, but I don't know. I'm not the one in charge. And so cosine 2 theta, oh, because it's 2 theta. Because that does cover, that goes from 0 to pi over 2. I mean to pi, because 2 times this is pi. So we're multiplying each of these by 2. So when I put pi over 6 in, that's actually, I'm taking cosine of pi over 3. When I put pi over 4 in, I'm actually doing cosine of pi halves. And then this would be the cosine of 2 pi over 3. And then this will be the cosine of pi, which is a -1. And so you have these values. So at 0, it's at 1. I mean at 3. So I probably should draw the circles first. I go out to 3 units. Okay. 2, 3. Yeah, I said. Okay. So when theta is 0, it's at 3. When it's at pi over 6, it's at 1.5, which is here. And when it's at pi over 4, it's on the pole. And when it's at pi over 3, I do a -1.5. And when it's at 2 pi, I go down to -3. So it looks like that. And it's repeated 3 more times. So if I rotate this 90 degrees, it's going to be here. And this one will be here. And it'll still go through the origin there. And then it's going to be here. And it's going to come back to here. So it's going to look like, so there's that. And then I'm going to go 90 more degrees. And so it's going to be here. And it's going to be here. And it's going to be back to here. And it's going to go to here. And then it's going to come up to here. So it's going to go like this. And then again, it's gonna start here and go to here and go back to here. And then where's that last one go? It's gonna go over to here. And then it ends up back there. So it's gonna look like this. I call those flowers or propellers, and they call them a rose. So here we have 1/4 of the picture. And so that's what it ends up looking like. There looks better because they have concentric circles and I don't. Okay. So that's a rose. And you can play with the different formulas for a rose. Right? It's symmetric with respect to the vertical axis. It is symmetric with respect to the horizontal axis and its respect to the pole. Because they're gonna, yeah, like that. This whole petal here is symmetric with that one there, and this one down here is with that one up there. So we're good. Because if I do the symmetry across each of the poles, I mean, each of the axes, this has this point down here, this one has this point over here, and this one has this point over here, and this one has this point over here, and this one has this point up here, and this one has this point up here. And so those are the points you, well, and then the ends of the petals. So that's symmetric there, and that is symmetric there. So what did they say? Reflect the portion of this graph about the polar axis and about the line to, all right, so they did it about the pole and across this line. What I did, I reflected across this line and across this line. Doesn't matter. Still get it the same place. Okay. So the rose curves are characterized by these two equations, where A is not 0. The graphs of the rows are shaped if n is even. Then the rose has 2 n petals. If n does not equal positive or negative 1, is odd, then it has an n number of petals. So if you're multiplying theta by an even number, then it will have 2n number of petals. So if we look back here, we were multiplying theta by 2 and we had 4 petals. If this was 3 theta, then we would have only 3 petals. But if it was 5n, then we would have 5 petals. But if we had 4n, we would have 8 petals. That's what this last statement down here is saying. I don't know. Y'all think that looks like a rose?
Yeah, it looks like some kind of flower.
Well, it just looks like just a flower. I don't know, that looks like a rose, but they call it a rose. And now we have r squared equals sine 3 sine 2 theta. They say verify that it's, yeah, if I put negative r in for r, that still gives me r squared. So I get the exact same formula. So I don't even have to do the other one where you substitute theta with pi plus theta. Because checking or putting negative r in for r does show that it's symmetric with respect to the pole. And so we only need to look at half of the values from 0 to pi. All right. There are no points on the graph for there will be no points on the graph in the second quadrant. This part of the graph will be vacant because 2 theta takes this angle down here and it ends up being negative. So you go along this, but it comes back down this way. So that's going to leave that empty up there. Okay, I see how that happens. So from the points where r is greater than 0 are plotted. Please notice you get plus or minus values along each of these angles here, because you're taking the square root. Oh, that's why you aren't gonna wind up there, is because sign in those makes it a negative sign, and negative square roots. Square roots of negative numbers are not real numbers. So that's a different one. Because what was the graph is with sine of 2 theta, and this is cosine of 2 theta, but this one's a sine of theta. Sine of 2 theta. What's it? 3 sine 2 theta. So I find out what this value is and I take its square root. Now, what I want to know is, how come we don't have anything down here? That's my question. Because if it's metric with respect to the pole, then this should have that part down here. Well, I'm thinking this is what's supposed to be. The graphs look considerably different, but they have the same numbers. But they changed the, okay, so this is a typo on their part. Okay, now. Okay. They're propeller shaped. Lemniscates. Lemniscates. Yeah, lemniscates. And that, I'm thinking they just didn't draw it in. It's supposed to be there. Because they're propeller in shape. What is that? Theta over what? It's a 4. So this is R equals E to the theta over 4. So E being raised to that fraction. In polar equations, in polar stuff, they use E quite a bit. Test for symmetry. R will never equal 0, so it never passes through the pole, right? Because if you remember the range of E is positive real numbers. So R will be a positive real number, which means this will never hit the pole. All right. And then R is positive for all theta. And R increases as theta increases. And R goes towards 0, but never equals 0 as theta goes towards negative infinity. Because you get fractions that are smaller and smaller and smaller. And as R gets larger and larger, R gets larger and larger as theta gets larger. So it's going to look like an exponential. The graph is going to look a little bit like an exponential, but yeah, it's a spiral. Got that. As you go on more and more negative, this spiral will come in, but it'll never reach the pole. It's like what happens to the person who is to something that's going into a black hole. You're spiraling down into it, but from an outside observer, it looks like you go into it, but the person who's actually doing that never actually goes in. But they do. But anyway, it spirals both infinitely both toward the pole and away from it. So this spiral is just going to get larger and larger. And so each time around the circle, it's going to get further away from the pole, exponentially further away from the pole. So here we have talking about lines passing through the pole in rectangular coordinates. That's called a direct variation. If a line goes through the origin, it's called a direct variation because the y value varies directly with the x value. There's nothing being added or subtracted. And so that gives us all the angle, all the lines that go through. It's just theta equals that whatever angle we're talking about. And for vertical lines, it'll be x equals theta, then r cosine theta equals a gives us vertical lines. It's just whatever r is tells you how close to the pole you are. And if r is positive, it's this way, and if r is negative, it's that way. And same thing here with sine, you get horizontal lines. And the r tells you how far away from the pole you are, either in the positive direction or the negative direction. And then with circles, all right, here they're saying if it's going to be tangent to the pole, then that's what these two look like, depending upon is if the center is on the polar axis or is if the center is on the vertical axis. And if it's centered at 0, then it's just r equals whatever the radius is. Where the cosine takes you away from the pole as well as the sine taking you away from the pole. They didn't look at the types when the center isn't and the center isn't. When the circle doesn't hit the center, or the center is somewhere not on either axis. And then we have the cardioids, the lamicons without an inner loop, the cardioids with an inner loop. Here we have a 4-petaled rose, a 3-petaled rose, and here we have the lamescape. Notice that the A value is a squared number. Every number is a squared number. It just depends on is it a perfect square or not, but it doesn't need to be in this case. Because A could be 1/2. All right. And so now we graph this. Oh, the lamescapes, the A and the B aren't equal. Is it the, or the what are the other ones called? The lemniscate, no, the in the cardioids and the lemniscates, especially the lemniscate. Well, no, with the cardioids, they are equal. They didn't. I don't remember them showing that formula that way. I guess they did. And so this is going to be symmetric with respect to the vertical axis. And so you look from negative pi over 2 to pi over 2, and then you just map the image across the vertical axis. Okay. You should recognize polar equation is the graph of cardioid. The period of sine is 2 pi. So you form a table using from, well, they used all the positive angles, but oh, they didn't even look at all the angles, did they? They just looked at the quadrantial angles. Realizing that 2 pi and 0 wind up at the same place. And so knowing what shape it's supposed to be, then you just draw the card away accordingly. I would look at the 45-degree angles as well, but because these two are matching points and these two are matching points, and that help only to help you scope out the what the curve is going to look like, get a more accurate drawing. Because this is not connect dots, it's not a straight line connection, it's a curve. Vectors. Complex plane and de Moivre, I have no idea how to pronounce that name, it's a French name. But it's a famous theorem in mathematics. Deals with complex numbers. All right, plot points in the complex plane. Convert complex numbers between rectangular form and polar form or exponential form. Find products, quotients of complex numbers. That's easy to do. And use whatever theorem. And so to use it, first they're going to tell you what it is, and then finding complex roots. That's the easy part. Okay. So a complex number z, we use the letter, the variable z for complex numbers, and when you're first introduced to complex numbers, we talk about it being in the form of a plus bi, but we can also write it this way, x plus yi. So the real part is on the x-axis and the y part is on the y-axis. The imaginary part is along the y-axis. So 2 plus 3i looks like the point 2, 3, where a -7 plus 2i. So I go -7 this way, and then I go 2i up. That would be this point. So it's just converting these two into an x and y, 2, 3, and plot that point on the regular coordinate plane, which we're going to call this the complex plane because it's dealing with complex numbers. Complex numbers are not well ordered. Where the real numbers are well ordered. You can put them in order, least to greatest. Complex numbers, we cannot put them least to greatest. The x-axis referred to as the real axis, because any point that lies on the real axis in the form of z equals x plus 0i just equals x, which is a real number. And the y-axis is called the imaginary axis because now the x is 0, and so z equals yi, which is a pure imaginary number. So we call this the imaginary axis and this the real axis, and any point outside of those two are called complex numbers or complex points. one of the classes I had difficulty in was called complex variables, where we had functions dealing with complex variables. Which I could take. Anyway. So plot the point concern with square root of 2i, square root of 2 minus I, sorry. So we go approximately the square root of 2 on the real axis, and then we go down 1 unit in the y direction. So it's just like, yeah, it's just like plotting the point square root of 2 negative 1. Just realizing we're dealing with complex numbers and not just real numbers. Now, magnitude or modulus. When we talk about the magnitude of a point, the magnitude of a complex number, or its modulus, that is how far is it from the origin? How far is it from here? Notice they put z in the absolute value symbol. This is called the modulus of the point z. So if you have 3 plus 4i, and I want to know its modulus, I write it that way, which becomes the square root of 3 squared plus 4 squared, which happens to be 5, the reason why I chose 3 and 4 in the first place. So that's just talking about this distance. And distance is positive, because we're not talking direction here. If I have a point down here, I still want to know how long that line segment is. And so I do the same thing, and you're going to get a positive number because the distance is positive. When we start talking about vectors, then we talk about direction, but here we're not. They didn't explain, did they explain z-bar? We didn't explain z-bar, did we? The magnitude of z is sometimes called the absolute value of z, because we use the absolute value symbol here. But z-bar, if z equals x plus yi, then z-bar, looks like a T, Thomas, z-bar is x minus yi. They're conjugates, right? Because when you multiply conjugate complex numbers, you get a real number. Because what happens here? We get x. Let me do 3 plus 2i times 3 minus 2i, and we do the multiplication. So that's going to be 3 squared, and then we had 3 times a minus 2i, which gives me a minus 6i, and then 2i times 3, which gives me plus 3 plus 6i, and then 2i times 2i, which gives me 2i times a minus 2i, which gives me a minus 2i squared. Well, the two middle terms go to 0. My first term is 9, and I'm subtracting 2i squared, which is 4 times I squared. Because when you're squaring something, you square everything. Well, by definition, y squared equals a -1. So this is a -4 times -1. So this becomes 9 plus 4, which is 13, a real number. every time you do this, you multiply a real number, a complex number by its conjugate, you get a real number. And then we just find the square root of it. So if I wanted to find what 3 plus 2i, what its magnitude is, then this is just the square root of 13. Which is a positive distance. I like complex numbers. Need to take that class again. Okay. When a complex number is written in standard form, z equals x plus iy, it is rectangular or in Cartesian form because xy tells us where the rectangle, where they are in the complex plane. But we can write it using polar form as well, where x equals cosine r cosine theta and y equals r sine theta. So it would be r cosine theta plus r sine theta times I. Or we would typically write the I in front of the sign just so we don't get confused that we're not multiplying theta by I, we're multiplying the sine of theta by I. And they factor the R out, so it's the radius times the cosine of theta plus I sine of theta. So this right here is this point. This is this number in polar form. This is a visual representation of what we're talking about. Because you have this angle here for this side. And you have the distance r to get to that. But the polar coordinates, I mean the rectangular point coordinates for this point are r cosine theta, comma, r sine theta. And then you just write it in that form, which is what they did here, where this is the x and this is the y. And then they did algebra to get it to look like this. We factored out the r and we just shifted the I to in front of the sign instead of after the sign. And that's something you do with I. If I'm multiplying I by a whole number or a decimal number or a fraction, we write it that way. But as soon as some other, like square root of 3i, we don't write it square root of 3i. We write it I square root of 3. So that way you know that the I is not underneath the square root symbol. Just like they're writing this I in front of the sign instead of after. So you know that this is the imaginary part. And it's not theta I. The magnitude, the argument, What's the argument? All right, if z equals r cosine theta plus I sine theta is the polar form of a complex number, the angle theta is the argument of z. Oh, okay. Things you forget over the years. So the argument of z is that angle that takes you up to that line segment. The magnitude of z is r. We look at the picture they had earlier, right? The picture we had earlier, where this is theta, this is r. Well, r is that distance here, which is the magnitude of z, its modulus. So, okay. For any real number theta, e to the I theta equals cosine theta I sine theta. This is Euler's rule, Euler's formula. You remember Euler? He's the guy who came up with the number E 2.71 whatever, 186 something. Some French dude.
And is that something to do with pi?
What? Nope.
Is that related to pi?
Nope. No, E is described as the limit as n goes to infinity of 1 plus 1 over n raised to the nth power. So what happens to this number? Well, this number approaches a certain value. The larger n gets, the larger this number gets, but it doesn't grow. It's bounded. Its growth is bounded. And so it grows to approximately 2.718. I think it's 6 and then a 2 here. I'm not 100% sure on that. I'm not even sure about the 6. Okay. So the larger n gets, the closer it gets to this magic number we call E. And Euler was the first one to describe it. And so we named it after him and gave it a letter E. And then his formula, he came up with this formula, which is why it's named after him. And he showed that E to the I theta is the same as cosine theta plus I sine theta. And so if you multiply n by r, you get any point on the coordinate plane. Where this right here is just on the unit circle, because r is 1. All right, so here we go. So if you know the angle and you know its modulus, you can write it as r times E I theta, where theta is the variable in this case, and r is a known quantity. When a complex number is written this way, it is said to be written in exponential form. So z equals r e to the I theta is the exponential form of complex number. All right, write this in polar form and exponential form. Okay, so first of all, we look at where it winds up. And that is negative square root of 3, which is somewhere in here, and then 1. So this is the point. So now we need to find out what R is. R equals the square root of a negative square root of 3 being squared plus 1 squared, which is the square root of 3 plus 1, which is the square root of 4, which is 2. So the modulus R is 2. This is the square root of 3, and this is 1. So we could use inverse tangent to find out what that angle is. See how they do it. Yeah. Oh, cosine equals x over r. Yeah, that's a better one to use, x over r. We already know that the cosine needs to be negative. And that's what? 5 pi over 6. So theta is 5 pi over 6 in this case. So in polar form, R is 2, and we have the cosine of 5 pi over 6 plus I times sine of 5 pi over 6. And in exponential form, you have R times e to the I theta. So it's going to be 2 times e, and we'll write the fraction first, 5 pi over 6 I. Yeah, I'm used to have it being written instead of I theta as theta I. R e to the theta I. That's how I've been used to seeing it written. So are they going to use the cosine and sine values and say this is 2 times negative square root of 3 over 2 plus 1/2 I? And this in here is what we call a unit vector, because that's how long, that's the modulus of this in here is 1 unit. Okay, so okay. So they did do it this way. So in polar form. And then in exponential form, I always write the I after the fraction rather than in front of the fraction, or I put it in the numerator. You could have written this as 5 pi I over 6 as the exponent. So 2 times e to the 5 pi I over 6, or 2 times e to the 5 pi over 6 I, or this way where it's 2 times e to the I 5 pi over 6. Either one of those ways is correct.
Say that again quickly.
Oh,
No.
please don't.
I. Okay. All right, so plot the point corresponding to Z and convert Z to rectangular form. Well, I would convert Z to rectangular form first and then plot it. Okay, and I would go from this. What's the cosine? What's the cosine of pi over 3? What does this equal? Off of the unit circle, what does it equal? What? 1/2. Plus. And what's the sine of that same angle? Isn't that the square root of 3 over 2? And I put I second in that case. And then I multiply in by the 4, which gives me 2 plus 2 square roots, 2i square roots of 3. I would write the I in front of the square root since there isn't a fraction anymore. And so this is what I will plot, the 2 square roots of 3. So the x equals 2 and the y equals 2 square roots of 3. And so 2 units this way, and 2 times the square root of 3 is more than 2, less than 3. So it's going to be up here somewhere. And this is 4 units long. And this is the angle. This is the angle pi over 3. We have the radius, and we have the angle, and we have r. We have r, that's r, and that's the radius. Yeah, this is more of a 45-degree angle. It's not quite where it needs to be. Actually, the 2 times the square root of 3 is closer to 4 than it's. But anyway. So yeah, so they see why I like to write the I here, because the way they wrote it here, it looks like you're taking the square root of 3i. We're not taking the square root of 3i. We're multiplying I by 2 times the square root of 3. So we would move that I between the 2 and the square root. Simply to keep it straight that the I isn't underneath the square root symbol. So we have 2 complex numbers. So when you multiply 2 complex numbers, we're going to multiply r sub 1 e to the I theta sub 1 times r sub 2 e raised to the I theta sub 2. So that means we're gonna multiply the r's together, r sub 1 times r sub 2. And because the bases are the same and we're multiplying them, we're going to add the exponents. So it's I theta sub 1 plus I theta sub 2. You can factor the I out. So it's I times the sum of the two angles. Well, oh, dividing. Okay. And if you're dividing two complex numbers, provided the one you're divided by is 0, then you're going to end up subtracting the two numbers. You do the division, but the exponents you're going to subtract. And again, you factor the I out. And so if you're multiplying two, you're multiplying the rate, the r's together, and you're adding the angles. And if you're dividing two complex numbers, you're dividing the r's and you're subtracting the angles. The numerator minus the denominator. So that's how it works. So if this one has a smaller angle, if z sub 1 has a smaller angle, then you're going to get a negative angle. It's okay, because you can always write it as a positive.
That's it. How do you finish it? Oh, he wasn't finished writing the equation.
Oh, okay. For z, r is 2. For that z, r is 2. Wait a minute. This should have been w. Right? Stupid people. Okay. And here, r is 3. And here, theta is 2 pi over 9, and here theta is 7 pi over 18. So the two points in in exponential form, the first one is 2e. They put I in front, so I'll do the same. 2 pi over 9, and that's what z is. And the w is going to be 3 times e to the 7 pi over 18. And I forgot to put the I in. And so the multiplying, I'm going to multiply 2 times 3, which is 6. So we have 6e. And then I'm going to add 2 pi over 9 plus 7 pi over 18. And I'm going to multiply that by I to get my exponent here. So that's going to be z times w. Yes, but I'm still working on that part. All right, so I need the denominators to be the same. So I need to multiply the first angle by 2 over 2, which gives me 4 pi over 18 plus 7 pi over 18, which is 11. I always do that when it's 11 pi. 11 pi over 18, because 4 plus 7 is 11. And so that's my exponent here is I times 11 pi over 18. And then z divided by w. Well, I'm going to do the 2 divided by 3, so that's going to be 2/3 e. And now I need to figure out what the exponent is. Instead of adding them, now I'm going to be subtracting them. So I'm going to do 4 pi over 18 minus 7 pi over 18, which is a negative 3 pi over 18, which is a negative pi over 6. If you can simplify your fraction, do it. Otherwise, you get a -2 on the test. And so now my angle is a negative 6 pi over, a negative pi over 6. I don't know how they're going to write it. Are they going to write it as a negative I pi over 6? Or are they going to write it as I times a negative pi over 6? Or do they write pi over 6 as 7 pi over 6? We'll find out. Because I would write this as a negative pi over 6i. Or 7 pi over 6. Because 7 pi over 6 and a negative pi over 6 winds you up in the same place. And so we're gonna look at how they do it, and because they should get the same thing I did. Unless I did something horribly wrong. And so, yeah, they went ahead and converted the two into their exponential form. And then they added the exponents and multiplied the coefficients. And got the I 11 pi over 18. At this point in your career in mathematics, you should be able to add and subtract fractions without too much difficulty. You're having problems with that, I can give you some help. Or go to Khan Academy and look for adding and subtracting fractions. They can help you with it. And now the dividing part. Okay. Oh, and then they rewrote it in polar coordinates. Okay. So the 6 here is the r on the outside, and the 11 pi over 18 is the angle for the cosine and the sine. Yeah, that's an easy thing to do. And the next one. Okay, is dividing. So again, we convert it to the exponentials, where we're going to end up subtracting the two angles. And yeah, they're going to leave it inside parentheses. Okay, so I times the negative pi over 6. And that's the same thing I had. I just kind of played with where you put the I, that's all. And if you're consistent where you put the I, then it shouldn't be a problem. And then they rewrote it in polar form. Now, cosine of negative pi over 6 and the cosine of pi over 6 equal the same value. But because these two angles have to be the same, they left the minus sign there. They didn't use the even nature of cosine to rewrite it. But you could. And then this negative sign you could pull out. So it'd be the cosine of pi over 6 minus I sine of pi over 6. The y value is going to be negative because the sign of negative pi over 6 is negative. And the cosine value is going to be positive because the cosine of negative pi over 6 is positive. So you still get the same point. It's just by convention, we write them with the same angle. I'm feeling old today. Okay. Oh, and they wrote a negative pi over 6 as 11 pi over 6. Okay. Which is what it is. And then they rewrote it again. So this here and this here are saying the same thing, just like these two are saying the same. The argument of a complex number is periodic. Periodic. What do I mean by periodic? Anybody have a clue? Sine and cosine are periodic. What does that mean? Huh? They keep repeating. The values you get keep repeating. So with sine of x, the sine of x, the y values are between -1 and +1. They keep repeating between those two. So it's periodic. And notice I always throw k in. K is an integer. That means k could be positive integer or a negative integer. So if k is positive, you're going around in a positive direction. If k is negative, you're going around in the negative direction. So 2k, I mean 2 pi k, I'm used to it being written as 2 pi k, where you're multiplying 2k by a number. Okay. So this is just how many times are you going around the circle? That's all. You still wind up at theta. If theta is pi over 4, then you go around once, and then that's adding 8 pi over 4 to pi over 4. So that's 9 pi over 4. And if I went around 3 times, and that's adding 12 pi over 4, so that'll give you 13 pi over 4. It ends up at the exact same place. So you keep going around and around and around, but you keep winding up at the same point. And I could have been subtracting 2 pi. So I can subtract it once, and I'm still going to wind up at the same place. I can just subtract it twice, and I wind up at the same place. Because that 2 pi means you're going a full circle. And you still wind up here. You're just changing the numbers, but it's still the same angle. It's just talking about how many times you go around in a circle. You get very dizzy if you go around too many times. Okay. Z to the n. That means when you raise z to a power. So, and that formula came in very handy when I took complex numbers. Stick it in my pocket and I forget. So if my point was 2 plus 7i, and I want to raise it to the 4th power. Well, let me pick something that I know the angle to. 1 plus 1i, or 1 plus I. So that means theta in this case is pi over 4. Because that's graphing the point 1, 1. So that's a 45-degree angle. And this distance is the square root of 2. So r equals the square root of 2, theta equals pi over 4. So if I'm going to raise this to the fourth power, this is going to equal the square root of 2 raised to the 4th power times e to the I 4 times pi over 4. So that ends up being pi, and that ends up being 4. So this is 4ei pi, or pi I. Either way. That's fun. Okay. Because otherwise, who wants to do all that multiplying? 1 plus I times 1 plus I times 1 plus I times 1 plus I. And this winds up being the point 4 times the cosine of pi plus I sine of pi. Cosine of pi is -1, so this is 4 times 1 plus 0i, so this is just 4. This is a real number. Is it? Because this gives me 1 plus 2i minus 1, right? Because I times I is -1 times the same thing, 1 plus 2i minus 1. So that's just going to be 2i times 2i, which is 4 times I squared. That should have been a -4. I should have gotten a negative. Oh, because cosine is negative, so that's negative here. I forgot. I even said it was -1, but I got multiplied and I wrote it as a positive. So that's a -4. So we get the same thing. So it's on the x-axis. And we started out here. We started at this point, we wound up over here. Because these 2 points, 2i, 2i, are here. So I'm multiplying that point by itself, and it gives me this point. Oh, -4. I'm sorry. I went the wrong direction. -4. I keep dropping that negative sign. That's a bad thing to do. So it kind of gets you there faster than having to multiply it all out. Because what if n is to the 27th power? Well, then this would be 27. And if that was pi over 4, then it'd be 27 pi over 4. And 27 pi over 4 is 24 pi over 4 plus 3 pi over 4, right? 27 pi over 4. I write it as 2 separate things. So I'm going to write the 3 pi over 4 first, because that's less than 2 pi. Plus, and this is just what is that, that's 6 pi. 6 pi, and 6 pi is 2 pi times 3. 2 pi times 3, where k is 3. And so that would be what we find. The radius was the square root of 2 raised to the 27th power times e to the I 3 pi over 4. So rather than multiplying 1 plus I, 27 of those together, and this wouldn't be too hard to calculate. That's 26 square roots of 2 times the square root of 2. I factored out 1 square root of 2. So this becomes the square root of 2 squared being raised to the 13th power, because 26 is 2 times 13, and using exponential properties. So the square root of 2 squared is just 2, and 2 to the 13th power is, I think, a 5 or 6 digit number. I think it's a 5-digit number. It might be 6 digits. I can't remember. I don't think I've ever done 2 to the 13th power. Okay. So that's in a place where I can't read. So we have 3 times the cosine of pi over 6, 3 times the cosine of pi over 6 plus I sine of pi over 6 being raised to the 3rd power. So this becomes r is 3. So that's going to be 3 to the 3rd power. This is theta, so it's going to be e to the I pi over 6 times 3. So multiply 3 times that angle. And so 3 squared is 27 e to the I of pi over 2. I pi over 2, or pi over 2i. So yeah, all right. They just converted this in here to the exponential form. And then the r is being raised to the 3rd power, and then the angle is being multiplied by 3. And it showed up underneath here, right where I had written. Okay. Which is what I wrote here. Well, the 3, I reversed that order. And so you still get 27 e to the I pi over 2. That's just really bugging me. It should be pi over 2i, but that's me. And then writing it back in polar form, 27 is the r on the outside, pi over 2 is the angle theta for cosine and sine. Going back and forth between polar coordinates and the exponential form, is it going back and forth between those two is really a simple process. So. So that's just 27i. Because the cosine of pi over 2 is 0. And the cosine of pi over 2 and the sine of pi over 2 is 1. So this is just 27 times I, which is 27i. So you're on the y-axis, the imaginary axis.
It's not negative?
Nope.
Doesn't the I become negative?
No. I represents the square root of -1. I squared equals -1.
Oh, yeah, you're right.
Yeah, there's a lot of fun iterations with I. When you raise I to certain powers, there's a pattern that develops. So when you raise I to powers, you either get 1, you get -1, you get I, or you get -I. So you have 4 outcomes, and they all depend upon what you're raising it to. All right, so write this in R 2 plus 2 times 1 plus I to the 5th power. Well, since I already used this earlier, we know this is the angle here is pi over 4. So what we have in here is I is e to the I pi over 4, and the 2, and we have a 2 here. So this is 2 times e raised to, well, no. Are they raising to the 5th power? Well, they're raising, got to be very careful here. They're not raising the 2 to the 5th power. They're only rising the e to the pi over 2. So for 1 plus I, what's its modulus? Because that's what R is. So we want to find the modulus of this, which we found out earlier was the square root of 2, because you have a 45 right triangle where the 2 legs are 1, so that means this is going to be the square root of 2. And so it's going to be 2 times the square root of 2 being raised to the 5th power. So this is what we're raising to the 5th power, not the 2. So now we're going to have 2 times the square root of 2 raised to the 5th power times e to the I 5 times pi over 2. And 5 pi over 2 equals pi over 2. Wait a minute, not pi over 2. Yeah. Because 1 complete circle is 4 pi over 2. That's the same as 2 pi. And we're adding this to it. So we're adding pi over 2 plus 2 pi, where k is 1. And so we're just dealing with the angle 2 pi, pi over 2. So I already simplified this part to e equals pi over 2. And now we need to evaluate the square root of 2 raised to the 5th power. Okay. So the square root of 2 to the 5th power is the same as the square root of 2 raised to the 4th power times the square root of 2. Well, the way the exponents work, I can rewrite this as the square root of 2 to the 4th power times the square root of 2. And 2 to the 4th power is 16. So this is the square root of 16 times the square root of 2. So this is 4 times the square root of 2. So here we have 4 times the square root of 2, which is 8 times the square root of 2, e to the I pi over 2. And then writing this in polar form, we have 8 square root of 2 times the cosine of pi over 2 plus I sine of pi over 2. And just like the other one, this goes to 0 and this is just 1. So this is going to give me 8i squared root of 2, or they're going to write it as 8 squared root of 2 times I. God, I hope I did all that correct. Where did I put it? Uh-oh. Okay. So they got the magnitude R is the square root of 2. And so you have the square root of 2 times 1 over the square root of 2 plus 1 over the square root of 2i.
Where can we go? Our bus is here.
Oh my gosh. And I'm almost 10 minutes over. I'm sorry. Somebody should have stopped me sooner. Go, go, go. Sorry,
I
guys.
feel rude when I stop you. Go ahead.
I couldn't hear you. There's too much noise in the classroom right now.
No, I didn't say anything, but like, if I did, I feel like it sounds like I'm trying to rush you.
I still couldn't hear you.
What's the plan for posting grades?
That's gonna happen today. And grades haven't been wonderful, so I have a plan for helping boosting grades. So if you
Thank
stay
you. Very
Because
much.
it's
I
the
will-
last day to drop today, tomorrow.
tomorrow,
So I
yes,
need to know.
I know, but I want the issue to be that you make a good grade on the 3rd and final. And then I'll have a project for everybody to do to help with low grades on the first 2 exams. And the project, you'll have a week to do it.
Yeah, I did pretty well on the 2nd grade because you were able to help me with that, so.
Okay.
I'm hoping. Yeah, I just really am concerned. I'm focusing on the tests coming up now.
Yeah.
Not more than the homework, right?
Well, and doing the homework helps you with the exams.
Okay, sounds good. Why?
Next week, I'm at the elementary, and then the following week and start the ongoing.
Sir, the test, what is it over? Like which of the segments we've been going over? Like for the homeworks, the point somethings.
Well, whatever we started with after the last test, that's gonna be on the next exam, which will happen after Thanksgiving.
Okay, and what will the projects be over? Because yeah, I haven't seen my grade exactly, but I'm sure it isn't the best.
I haven't posted the grades for this class yet.
No, I know, but I was saying, well, like for the project, that's supposed to help boost our grade a little bit. What will be over?
Well, it'll be over the material for exam 2.
Oh, okay. Okay, that works.
So it'll boost up those grades. Now, I'm also gonna have something planned to help with the grades on the first exam.
Okay, good. Yeah, because I don't want to drop the course because I kind of do. Like we're already
No.
far into it.
And here's the deal, this has been a bad semester for me. For whatever reason, things haven't gone great for me this semester, so I'm terribly behind on grades. I'm terribly behind on doing things. I haven't gotten paperwork done for my department. So I'm just behind. And so I don't know what the reason is, but I got behind and I've stayed behind. So unfortunately, y'all are being punished for it because I'm not helping y'all like I usually do. And so that's what I'm gonna do now. I'm gonna come up with some things to help you boost those grades. If your grades are low and you need to bring them up, I will give you something that can do that.
Yeah, I'll
One
definitely
of the things that's very important on these projects is to show all of your work. Because people haven't been showing their work. People haven't been giving me all of the problems. Like I had. And then graph. I had at least one person only send in one of the 3 problems. The first 2 problems were worth 40 points apiece, and the third problem was worth 55 points. So I had one person just do the hand in the third problem, and they didn't even get it all correct because they didn't show a lot of their work. And plus they were missing a total of 80 points from the first 2 problems. Now, I don't know if they did those and just didn't and thought they had put it in the PDF file and sent it to me, but it didn't get to me. So, staring at a bright light, I need to stop that.
and when will you have the project out, like open to do?
I want to get it up there before Thanksgiving weekend, and so, but I need to tell everybody about it. Because I don't want it to interfere with working on the next exam. And I think we have one more week before Thanksgiving week, and so that's, ooh. I've told all my college algebra classes about this, but I haven't told my pre-calculus classes about this. So I'll be sending out an email. I'll probably post it on Monday, and I will want to have it back by noon on Friday.
Oh, okay.
So you have 4 full days to be able to work on it. And I have to see all of the work. And that doesn't mean you pull it up online and you copy what they tell you. I want you to be able to work the problems. So consider it an open book exam.
Over the
but it's
4
just
days
gonna-
that over the 4
Yeah,
days that it'll be open,
I-
can we ask you for help, like in your tutoring hours?
Yeah. You can even ask me during class time.
Oh, okay, okay. Well, I won't do that because I do get really confused when you're explaining things, and I feel like I'll take up most of the class time and we won't really get over the chapter like that we're on.
I expect everybody to get 100 on it. Okay? That's my expectation. But if I don't see all of your work, even if it's an obvious answer, in what I was doing with my college algebra classes. All right, so if you have something that is x to the third plus 3x squared minus 2x minus 9, and this is your function, what is the y-intercept? The y-intercept is 9, -9. Well, you need to tell me how come you know that. Well, that's saying f of 0 equals -9. That tells me that -9 is the y-intercept. So I need to see this for them to get full credit there, for them to get any credit there. Because that's what I'm going to do on this. Either I see all the work and you get the correct answer for full points. If all they said was that not -9 was the intercept, they don't get any points for that. But if they show me this, but they get another number other than 9, I'm still going to give them credit for it, but not full credit because they got the wrong number. That making sense?
Yeah, it's on the rubric you put online as well.
Yeah, yeah. But the rubric for this is going to be more, do you have everything there? Yes, full credit. Do you have everything and you have the correct answer? Full credit. Do you have everything there, but you got the wrong answer? Then that's half credit. So it's either everything is perfect, so you get the 10 points, or it's not, you did all the work properly, but you got the wrong answer, so that's 5 points. You gave me the correct answer, that's 1 point without any work. You gave me the wrong answer without any work, that's 0 points. So you see how my grading scheme is going to work? My grading scheme on this is going to be very severe. Because you can check your work online, you can check your work with me. I will just say, well, rethink what you did here. I will point you in the right direction, or I'll have you look at something and rethink about it, but I won't tell you how to do it.
All right, that makes sense.
Okay.
All right, sir. Have a good day.
You too.
I'm gonna.
And don't forget Khan Academy is very helpful.
I don't know what I'm gonna do, but I'll figure something out because today's my birthday.
Huh?
Said today's my birthday.
Well, happy birthday.
Well, thank
I
you.
hope it's a good one.
I was trying to find a dress shirt yesterday and a freaking drunk driver hit me and my brother's car.
Uh-oh.